Okay, so we have a picture of what an expanding universe looks like, but can we say any more? What we want to know is how would we learn about the distant past of the universe? We'd have to watch things at great distances. We talked about the great importance of pulsars. They are the brightest things we see in the universe, so we can see them at large, cosmologically significant distances, not negligible with respect to c times h0 inverse. And so we can use them to see some way into the past. Can we see even farther? All of our models had this weird property that at some finite time in the past, the size of the universe was zero. Notice that this has nothing to do with the picture that says that the universe was a small, dense marble. That is the picture from the point of view of someone outside the universe. I've never been outside the universe, and I have no plans to do so in the foreseeable future. As a physicist, all I mean is that the density was infinite. If the initial size of the universe now is infinite, then multiplying it by a very small number, you still get an infinite universe. It's just as infinite, except it's much, much, much more dense. And as we'll see, that is that little bit at the beginning that we'll spend as much of next week as we can trying to understand. But this was a very bizarre situation that the entire visible universe, all the billions of light years away that we can see, emerged from very small distance. This was derisively called the Big Bang. And some evidence was needed to convince physicists that this was real. And we're going to go back in history a little bit. We were at the 90s. Let's go back to the 40s, where George Gamow, with his student Ralph Alpher in the 40s, had this brilliant idea that said, look, if we were to take the current universe and compact it, contract it, which is essentially what happens if you look back in the dim, distant past, then densities in the very, very early universe were very high. And because in running the movie backwards, we have contracted things, temperatures would have been very high. It would have been very hot and very dense. What's good about very hot and very dense places is very hot and very dense places is where protons can fuse to form hydrogen and lithium and beryllium and heavier elements. So Gamow's idea, and he and Alpher worked on this idea, was that maybe the early dense universe is where nucleosynthesis took place, where the observed, to the precision he knew them in the 40s, prevalences of various elements in the universe or in the solar system were generated by the processes of nucleosynthesis in this dense early universe. Now, it turns out that this doesn't work. It doesn't work because the universe was only very, very dense enough, like the interior of a star, and hot as the interior of a star, for a very short time. It didn't sit there as a star does for billions of years, fusing hydrogen to helium. It had to do this very rapidly. And so the fusion past helium and perhaps trace amounts of lithium would not work. There was a problem with the triple alpha process that made it impossible for fusion past helium and perhaps a little bit of lithium to have successfully happened in the early universe. And so this idea that in the first few minutes of the universe or few seconds of the universe's existence, nucleosynthesis, this is where all the heavier elements were made by fusion, was a failure. There was another failure, which is that the estimates of the Hubble constant in the 40s were not nearly as precise as those we have today, and the Hubble time was estimated then at 1 billion years, which is a worse contradiction than the ages of the oldest globular clusters. That's younger than the age of the Earth. So there was a problem with the Big Bang model, and this prompted the proposal of an alternate model by Fred Hoyle and others in 1946. It was called the steady state universe, which is homogeneous in time as well as in matter and space. And since we observed, Hubble had observed in the 20s an expansion, that meant that in order to preserve, what Hoyle suggested is that the density of the mass density rho is not only constant everywhere in space, it's also constant in time. And since the observed matter was receding, that meant that new matter had to be continually created. This sounds like a crazy theory. At the time, it was a much more sensible theory than what Hoyle derisively called the Big Bang. And in fact, it prompted Hoyle, together with Burbridge, and Fowler, to propose in 1957 the modern theory of stellar nucleosynthesis, the fact that all heavier elements were in fact produced by and large, modulo supernovae and so on, in the interiors of stars. And this is a very successful theory, in particular, as I mentioned when we talked about stars. This led Hoyle to propose a resonance in the spectrum of beryllium that was subsequently discovered, and so was a great success. Now, this allows us to explain all the trace elements of heavy metals, elements past helium. But 1/10 of the atoms in the universe, approximately, are in the form of helium. That means that about a quarter of the mass, since helium is heavier than hydrogen, about a quarter of the mass of the universe is in the form of helium. A quarter of the mass of the universe has not yet been in a star, let alone been fused. Remember, stars fuse typically 10% of their mass to helium. No amount of stellar nucleosynthesis could explain this. Perhaps Gamow was right. So physicists had, by the 60s, were accepting the Big Bang model, but we're still trying to figure out whether it's possible that fusion of hydrogen to helium occurred in the early universe. And if it occurred in the early universe, the great thing is that the answer to where it occurred is not in a star, but everywhere, right here. Hydrogen was fusing to helium, because right here was part of that very dense early universe where, when you follow the nucleosynthesis models, and we'll talk in much greater detail about this later, and we'll return to Gamow and his ideas, the temperature at the time when helium was formed would have had to be about 1 billion Kelvin. That's a little higher than the interior of the sun, but that's because you have to get it done rather rapidly. Turns out that at higher temperatures than this, the deuterium, which is an important intermediate stage, is broken up by photodissociation, and at temperatures much lower than this, the rates would be too low. And you need a density, well, on the order of about 1/100th of a kilo per meter cubed. We'll talk later about how these numbers were arrived at when we talk about modern theories of nucleosynthesis. This is a 60s version, or 50s version. And when did that happen? Well, that's not too hard. You give me the known density of baryons, because this is baryonic matter that's fusing, so the density of protons at the time that helium was being fused. I know the density of baryons today. You can look it up in our previous calculations. And if you make the ratio, remember that rho of t at any time in the past is rho 0 a of t to the minus 3. So to find how what the scale factor was at the time when helium was fusing, when the density was this, you find that the scale factor was 1 billionth or 3 billionths. So this is a long time ago. Densities were much higher by the cube of this. Indeed, that is the ratio of current density to this. And for that brief time, when the density was this high, when the scale factor was this small, way at the beginning of the universe, hydrogen would have fused to helium everywhere. And now, at that time, that fusion was producing gamma rays in equilibrium with a radiation bath with photons, a black body spectrum of temperature 1 billion K. What happened to those photons? Asked people. Well, those photons, if they were still around, would no longer be gamma rays because, of course, like everything else, they would have been stretched by a factor of 1 billion or so. And so we remember that black body radiation stretched by 1 plus z is black body radiation at a temperature lower by 1 plus z. 1 plus z is the inverse of A. And so the current temperature that these photons would exhibit was computed by Dickey and others and predicted from these data to be about 3.5 degrees Kelvin. So these are no longer gamma rays, these are now microwaves. Now, radio astronomy had started. We talked about Jansky and others. And in 1960, Dickey realized that he was a radio astronomer. He had invented something called the Dickey radiometer. And his idea was that he could construct a Dickey radiometer and try to see this radiation. Now, Dickey was working at Princeton University, and unbeknownst to him, about 30 miles away at Bell Labs in New Jersey, Arno Penzias and Wilson were working on the early version of satellite communication gear. You can see that it's an early version in this image on the right. They had this great big horn antenna. It was very directional, so you could aim it at a satellite. And they discover noise. Sounds like Jansky. They discover a noise, but their noise is not periodic. Their noise is constant. And it turns out that no matter where you aim the antenna, you get the same noise. There's a amusing story where to try to clean, you clean the contacts and you look at all the electronics, and at some point a family of pigeons had made its home in their antenna, and they spent a happy couple of days scraping bird droppings off the antenna, thinking perhaps this was somehow influencing their signal. Eventually they realized that because it comes from all directions, their source that they're detecting cannot be some local radio station, it cannot be terrestrial, cannot be in the solar system. But if it's coming from space, from some radio source in space, it would be repetitive with a sidereal period. It seems to be coming from everywhere, and somebody mentions to them that Dickey is thinking about such things, and so they call Dickey, and in fact there's a conversation, but the apocryphal, probably great story is that Dickey walks into a group meeting where they had been designing the Dickey radiometer and says, "Never mind, we've been scooped, the radiation has been discovered." What Penzias and Wilson had discovered, in fact, was the relic microwave radiation from the hot, dense past of the universe, and it is coming at us from everywhere because it was hot and dense everywhere. In fact, this is light that we are seeing, we now know, from about 13.8 billion years ago. We are seeing light that was emitted in some high-energy processes 13.8 billion years ago, 13.8 billion light years away or farther, as we will see because of the expansion, and has been moving through the universe and redshifted since then to the point where those former gamma rays are now microwaves, and this is what we call the cosmic microwave background. This, of course, demonstrates that a hot, dense past for the universe is not some silly Big Bang, it's a fact. And the properties of the cosmic microwave background are very exciting. We will return to it in the future. The first thing is that it is a black body spectrum. The fit here is precise to unbelievable precision. This is the observed data points from the COBE satellite in the 90s, and this is a black body spectrum at a temperature of 2.7260, so not exactly 3.47. We'll have to modify the model that Dickey was using, or that Gamow was using, a little bit, but the temperature of the universe is about, or of the radiation in the universe, is about 2.72 Kelvin. Not exactly absolute zero, but not a lot above it. It is indeed isotropic. It's coming at us from all directions. It is isotropic, we learned in the 90s, to 1 part in 100,000. This is perhaps the best validation of the cosmological principle you could imagine when you look to the farthest distances, deeply into the past of the universe. What does the universe look like? It looks the same in all directions. This is precisely the statement of the cosmological principle. And this, as I said, is the oldest light still around. We'll discuss details of when it was emitted later. But also the entire universe is full of it. So there is some energy density. We will convert energy to mass, reminding ourselves that when we do relativistic cosmology, then gravity couples to energy in all forms, including mass and radiation. So we can ask how close to criticality perhaps this collection of photons is what makes the universe critical. Remember, the theorists like omega to be 1, and we had omega equals a quarter. So you can ask, what is the density of energy in the photons? And the energy of densities in a photon field that is a black body spectrum going everywhere from everywhere else, well, you're not surprised that it has a sigma t to the fourth in it. Dimensional grounds give you a 1 over c. And then there's a geometric factor g that in the case of photons turns out to be 2, that counts the number of states a photon can have given a direction of propagation and a wavelength. So this is 2 polarization states, if you like to keep track of that. And we know the temperature, we know g is 2, we know the speed of light, we know the Stefan-Boltzmann constant. You can plug in, divide by the critical density that I gave, and photons are not going to make the universe critical. Omega in matter, mostly dark, was about a quarter. Omega in light is about 100,000th. So photons make a negligible contribution to the energy density of the universe, but as we shall see, this was not always so. The following picture is perhaps a great idea. This is the full sky image of the cosmic microwave background, where colors indicate the different temperatures, but it's all the same color. Yes, this is because the sky is all exactly the same temperature to within 1 part in 100,000. The universe is very precisely isotropic. but not exactly isotropic. In fact, when in the 90s we got more exact data, we found that in fact, this is a map drawn by astronomers, so you're not surprised that blue indicates the hottest regions, red indicates the coolest regions. One side of the sky is warmest, and the other side of the sky is the coolest. The sky is not isotropic, there's a preferred direction. What would you say to that? Well, of course we know what that means. Remember that a radiation field only looks isotropic if you are to one observer. Because if I see light from all colors, from all directions, with the same black-body spectrum, someone who's moving relativistically in that direction will see blue shifted light from that direction, and red shifted light from that direction. He will think it's hotter over there and cooler over there. There's a unique rest frame. Oh, it's the Hubble frame. Remember, the Hubble flow picks a rest frame at every point in space at any time. And what this is telling us is that we are not in that rest frame. We are actually moving relative to the rest frame of the universe, which is the cosmic microwave background. And after subtracting the motion of the sun around the Milky Way and the Milky Way in the local cluster and so on, we find that roughly what this expresses is a motion of our entire local cluster at a speed of about 600 kilometers per second in a direction roughly towards Virgo. So next time you go outside, look up at the constellation Virgo. There's lots of fun galaxies you can look for. But more importantly, that's where you're headed.